guys, welcome to Kinemarc, and this lesson is on basic mechanics. We're going to look at dimensional analysis and operations involving units of quantities. Okay, so we start with dimensional homogeneity. So dimensional homogeneity is about equations where each term has the same unit. So an equation is called homogeneous if each term in the equation has the same dimension or carries the same unit. And these kinds of equations are very important because, well, in the first place, in mechanics, all equations describing a physical process are dimensionally homogeneous. So we use this as a partial check for algebraic manipulations of equations. So if we manipulate an equation a bit, we can check if all the terms in that equation have the same units or are dimensionally homogeneous, and then we know it's a partial check. We know at least we are on the right track. So one of such equations is one of the kinematic equations, or should I say kinemarctel equations. Really common. S equals Vt plus half At squared. Okay, so we are going to check if this equation is dimensionally homogeneous. Remember, the check is that every term should have the same units or should have the same dimension. So the terms are separated by additions. So this is one term and this is one term. This is a distance, so its unit is meters. This is velocity times time. The unit for velocity is meters per second. The unit for time is second. Per second cancels second, so we have meters. And then here we have half times acceleration, meters per second squared, and then time squared, so second squared. Second squared cancels second squared. And constants are dimensionless, so this has no effect on the unit, on the dimension. So again, we have meters. So there's meters, there's meters, there's meters. So this equation is dimensionally homogeneous. All right. So next up, we try to check the dimensions of common quantities. So these are all basic quantities. Length, meters, so let's have dimension L. Mass, M, and then time, T. Now area is some length times some other length, so it's going to be length times length. So we have L squared for area. So acceleration is a change in velocity over time. So it's some velocity over some time. I mean, a difference in velocity, whose dimension will be a velocity, and then over some time. We know velocity is meters per second, so some distance per some time, so L per t. And then this velocity is changing over some time, so this is over some time. So L per t divided by t then becomes L per t squared. So acceleration has a dimension of LT negative 2. We know force is some mass times some acceleration. So we have mass multiplying, we already have acceleration here, so we just multiply LT negative 2. Now pressure, we know pressure is some force over some area. So we have force here, MLT or ML per t squared, dividing some area, and we already have area to be L squared, so L squared. Evaluating this, we just have L dividing L squared, we're going to have per L, or L to the power negative 1. So then we have L to the power negative 1. And then for moment, we know moment to be force, some force times some distance. So we already have force to be MLT neg 2. And then we multiply this by some distance, perpendicular distance, so it's still an L. So then we have L multiplying L, so we have ml squared. Now energy or work, we know, just pick for each of these quantities, just pick any formula you know, right? And so for energy, we know force times distance to be energy expended or work done. So we already have force to be mlt neg 2, and then we multiply this by some distance, so again it becomes L squared, so L squared. And then power, we know power to be some energy or some work done over some time, so it's this formula we have here, or this dimension we have here, ml squared per t squared dividing some time. So we have t to the power negative 2 dividing t to the power 1. We're going to have t to the power negative 3 over here. So then it's t to the power negative 3. Okay, so we test our understanding with a very interesting question here. So we are to determine the dimensions of I, R, W, M, and C in this equation here. And we are told that x and y are lengths, so their dimensions are just going to be an L. And then we are told P is a force. We know for any force the dimension is mlt or ml per t squared. And then we are told E is a force per unit area, so we expect that the dimension of E is mlt, our force, dividing an area L squared. So L dividing L squared, we're going to have an L to the power negative 1 here. Okay. Okay, so moving on, how do we approach this? Now, what do we know about dimensionally homogeneous equations? We know that for each term, or each term in the equation will have the same dimension or unit. Now, look at this. EIY will have the same dimension as Rx cubed and will have the same dimension as the entirety of Px minus A all cubed. The same dimension as this, this, and that. We also know that you cannot add two quantities that have different dimensions. So if we're having an addition or a subtraction of any two quantities, we are rest assured that these two quantities have the same dimension. So if you look at this particular term, P multiplying the cube of x minus A, once we are having x being added to or being subtracted from A, x minus A, then we know that x and A have the same dimensions. If you have any quantities at all, say some two angles, theta 1 minus theta 2, if you know theta to be in degrees, then surely theta 2 is in degrees. If theta 1 is in radians, surely theta 2 is also in radians. So we are rest assured that if any two quantities are adding or subtracting, then they have the same dimension. So the question tells us nothing about the quantity A, but the mere fact that A is being subtracted from X, then A has the same dimension as X, and we are told that X is a length, so definitely A is also a length. So A has a dimension L, or a length. All right, so A has a dimension L. Now moving on, we see C sort of alone here, and Rx cubed. We know that Rx cubed is going to have the same dimension as C, so we can confidently say that C is dimensionally equal to Rx cubed. Now we know X to be a length, so this is in fact RL cubed. So we know C has the same dimension as RL cubed, but we don't know what R is. Is it a force? Is it pressure? Is it some moment? So we're going to have to figure R out. But you know, we make use of our knowns to find our unknowns. If you compare Rx cubed to P multiplying the cube of x minus A, we already know that x and A are lengths, so both x and A have the dimension L. That means that this entire bracket here has a dimension L, because if you subtract a length from a length, you get a length. So this is actually P multiplying L cubed, or a force multiplying an L cubed. So we are going to compare our Rx cubed to this force multiplying L cubed. So in fact, our RL cubed has the same dimension as our P. We are told in the question that P is a force. So let's just say our force has a dimension F, and then this quantity has L as its dimension. So our RL cubed is in fact has the same dimension as FL cubed. So obviously R is equal to L just by comparing both sides. So our R is in fact a force. Now we can say that our C also has the dimension R is an F, so FL cubed. Now, so we found C, we found R. Now we can compare C to our Wx to the power 4 here. We know X is an L, X is a length, so our C has the same dimension as this Wx4. X is a length, so L4. So we already know our C to be FL cubed, so we say FL cubed is in fact equal to WL4. So we can compare both sides and find out the dimension of W. So we can simply express our WL4, because we want it to resemble our left hand side. We can express our right hand side as W times L cubed. So as you can see here, we have L cubed here, L cubed here. So our WL is in fact a force. So our WL is a force. So our W is in fact some force dividing some length, some force per length. Okay, so that also gives us our W. Now we know W. Now we need to find M and I. Okay, so we have L squared here. We can simply compare that to our FL cubed. So we say our L squared, is it squared? Good. Our ML squared is simply equal to the dimension of our C, which is FL cubed. So just like we did for W, we can express this, or we can simply just sort of make M the subject, M equals FL cubed, L squared, so we divide by L squared. So we just have M to be equal to FL. So our M is simply FL. Okay, so that gives us our M. Now we need to find I. So where can we find I? We have I in this quantity here, EIY. So we can compare that to our FL cubed. So for space, our EIY has the same dimension as our FL cubed. And in the question we are told that our E is a force per unit area, so it is an F per L squared. So our E is in fact a force per unit area. We can write this as F L, or F per L squared. So this multiplies our Y. We also told our Y is a length, and then our I should have the same dimension as our FL cubed. So we just simplify. L cancels this, so we have Fi per L should be FL cubed, and then this is just a matter of simplification. So our I should be equal to FL cubed. Our F moves to this side, so we have a per F, and our per L moves to this side, so we have an L. So our per F cancels our F. Our L cubed just multiplies L, so we have L to the power 4. So our I is equal to L to the power 4. Right. There are many approaches you could have taken to get all your quantities, to get the dimensions of all your quantities, but this works. So in our next video we shall cover units and operations on units and quantities. See ya.